Today I'm going to be talking about our work with one of my absolutely favorite collaborators, Jana Gevertz, on guiding model-driven combination dose selection using multi-objective synergy optimization. Synergy is a very exciting concept. We all want synergy everywhere, always. But how do you actually quantify it? Well, synergy is defined relative to additivity. If your combined effect is greater than what is expected in the additive case, we call that synergy. If it is less, we call that antagonism. Seems simple enough. Unfortunately, it is not. And that is because the definition of additivity has been at the center of controversy among leading researchers of the topic for the last century. And that is because additivity does not simply mean adding things. For example, if you have one drug that kills 60% of cancer cells and the other drug that kills 50%, well, additive effects of the drugs at their saturating dose will not result in 110% of cells being killed. And there exists an overwhelming number of divergent definitions of additivity in the literature, which makes quantifying combination effects surprisingly challenging. There exist two main classes of metrics to define additivity. One way is to define additivity via efficacy or output. The most well-known metric of these is Bliss additivity. It assumes additivity defined by dose independence, and it sets a very high bar for additivity. You can also use high single agent, which assumes that the combination is additive if the efficacy of the combination is at least as good as the most efficacious monotherapy. This one actually sets a pretty low bar for defining additivity and therefore synergy. You can also look at additivity defined via potency or input. The most well-known metrics of these is low additivity. So that's when additivity is defined by assumptions of dose equivalence. That essentially means that the drugs can be virtually interchangeable up to some constant. This one requires certain assumptions to hold in order to be relevant. And then we introduce a new metric called lowest single dose, and that is essentially our potency-based analog of high single agent. That is, we assume the combination is additive if the potency of combination is at least as good as the potency of the most potent monotherapy. The main thing that you need to take away from this and pay attention to whenever we talk about any of these things is the coefficient of interaction. It's this fraction where you have the ratio of what the metric is predicting versus what you are actually observing. So if the effect that you observe is greater than the one predicted by the metric, then you have synergy and you have coefficient of interaction less than 1. If it is smaller, then you have antagonism, that is coefficient of interaction is greater than 1. Obviously, if they're equal, then you have additivity. So what we want to see is coefficient of interaction by any metric to be less than 1. Okay. Well, yes, there are a lot of metrics, but maybe they all converge. Maybe they actually predict the same thing. Let's check. We apply this to this toy model. Very simple, very non-realistic, but still helpful here. So you have some kind of a tumor growth that is logistic up to carrying capacity, and you have two kill terms, assuming D1x is proxy for kill by drug 1, D2x squared is proxy for being killed by drug 2. So we assume one of them is maybe linear kill, the other one is quadratic. Okay, so we create these plots. On the x-axis, you have the dose of drug 1. On the y-axis, the dose of drug 2. And let's check what synergy of efficacy by Bliss predicts. So we'll look at this and it says, okay, so if we vary these doses and calculate our combination indices, all combinations are predicted to be additive to antagonistic, since coefficient of interaction is greater than 1. Okay, interesting. Let's look for synergy of efficacy according to highest single agent. Well, here the situation is very different. Again, doses are all the same on the x-axis and on the y-axis, but all of these combinations are predicted to be additive to synergistic because coefficient of interaction is less than 1. And also, region of maximal synergy over here is overlapping with the region that Bliss quantifies as maximally antagonistic. Well, that's not amazing. Well, maybe we have better luck with synergy of potency. Let's look at that. Okay, so this is lows. Again, same doses, everything is the same. We're just calculating the coefficients of interactions according to different metrics. Here we have the combinations range from slightly antagonistic at low doses to somewhat synergistic at high doses. And the classification seems to be more sensitive to drug 1 dose. So this one is more of a change here, okay. And then according to our new metric, most combinations are antagonistic with region of near additivity at low doses of drug 2. So here, this is really driven by drug 2. Well, this is not amazing. And it is known that this is not amazing. In fact, in a recent meta-analysis, it was found that the majority of assigned synergistic and antagonistic labels were found to be unique to a certain metric. And this illustrates that the choice of synergy metric influences the conclusions drawn substantially, to say the least. If I had a team or if I had a project and I had to pick some combination of doses, I would not be able to do this from this information. So what do we do? Well, we propose the following approach: to use multi-objective optimization of synergy of potency and efficacy. Okay, this is going to be a little messy, but it's going to be quick and painless, I hope. So multi-objective optimization problems have multiple objectives that need to be optimized simultaneously over the set of some feasible decision vectors. Okay, for example, we want to minimize tumor size and toxicity for combination therapy over some set of plausible doses. We call that the design space. And if there's a single point that minimizes both of these, this would be the optimal solution. Of course, generally there are different optimal points for each objective. For example, here we start okay. So let's look at here. This is the minimal toxicity, which is 0 dose of both drugs. Well, this is also minimal efficacy, not really optimal. Maybe you want to minimize tumor size. That's the highest doses of these two guys. Well, that is probably also going to give you the highest toxicity. And so this is also not that easy to do. This is where we talk to our friends in economics and we use the concept of Pareto optimality, which is the set of all decision vectors for which one objective cannot be improved without the other objective worsening. We call these non-inferior solutions. And so to find a Pareto optimal solution set requires mapping points from our design space, so the actual doses, to criterion space, which would be our combination indices or some kind of impact on outcome. So for example, here would be minimal tumor size, here would be minimal toxicity. Another way to look at this, maybe this would be synergy of efficacy, and maybe this would be synergy of potency. Okay, so the way that this would work, we take a dose and we map it onto the space. Okay, so you have 0, 0 gives you largest tumor size but minimal toxicity. Okay, this one gives you smallest tumor size but largest toxicity. And then you go through, you check all of these doses and you map them onto your criterion space, which is your impact on outcome. Eventually you get a plot that looks kind of like this, a plot of non-inferior solutions on a Pareto front. Okay, so what does this look like? This, for example, would be an inferior solution because there exist solutions that minimize objectives on both criteria. So this is not a good choice. This one looks a little better. This is a non-inferior solution because there is no solution that makes both objectives smaller. If you change that, well, you will compromise the other objective. Okay. This one is also pretty good. It makes objective 1 smaller, but at the expense of objective 2. Here it would be make objective 2 smaller, but at the expense of objective 1. So we go through all of these and we build what is called a Pareto front. That is a set of non-inferior points that solve a multi-objective optimization problem. And each solution on this Pareto front corresponds to a point in design space. Remember, our design space is basically a combination of doses of drugs 1 and 2. And then whoever is making the decision will decide which solution on the front they desire. For example, if they can afford to have slightly higher doses, maybe they will choose, I don't know, this point. If they cannot, maybe they'll choose this, etc., etc. And then they select the dose that will correspond to that point, which they then want to check out. Okay, so now we must decide which synergy objectives we want to optimize, that is, which combination indices to minimize. But didn't I just show you that the metrics can be so inconsistent? Which ones do we choose? Well, we propose using all of them. We will build 4 Pareto fronts and find doses that overlap on all the metrics. So it would look something like this, and then we'll read off the corresponding doses from all of those, and then find the ones that overlap. Okay, so this is our theoretical basis. Let's find an application. We're going to try to do an application to some real data. So this is an example from the literature of a combination of pembrolizumab, which is a PD-1 checkpoint inhibitor, and bevacizumab, which is an anti-angiogenic agent. It's also known as Avastin. These guys, they had some experiments, so they tested just one combination dose. So they have monotherapy and they have combination therapies and 2 cell lines. Okay. And they have particular schedule and dosing for each of the drugs. You plug in whatever you need, whatever data you have. Drugs were tested, as I said, in monotherapy and in combination. And now what I want to do is to find, did they do a good job? And can we actually guide them to a better combination? So what do we need for this? Well, we need the PK data. So here PK was parameterized separately using just literature data. Just found some PK data for pembro in mice in Lindauer et al. Paper from 2016. Parameterized it, very standard. So okay, great, we have the PK piece. Avastin also found another paper, Lin et al. From 1999, mouse PK. This was better described by one compartmental model. Okay, that's pretty good. Again, pretty easy to do. And then for the PD part, so we have the following models. So we have some tumor growth, and then I have my negative terms. So, okay, killed by drug 1, drug 2, or some combination of the 2. This now has this transient damage compartments, like Simeone model. Doesn't really need that here, but we can have it in case this is relevant for your particular case. Okay, so this is the model, and this is the data. It's pretty standard. We have, so cell line H1299, this is P53 negative, so we have monotherapy pembro, bev and combo, and this one, same thing, so A549, monotherapy for pembro and bev and combination. Now we are ready to apply our method and to find optimally synergistic combination doses for these 2 drugs. Okay, so we now apply our method. Let's see the application for A549. So we build these beautiful plots. These are the red dots. These are our Pareto fronts. So then we have the output of this plot, which is the number of times a dose appears on each of the Pareto fronts. This was the original protocol. Okay, well, it looks like there are actually a number of doses that are Pareto optimal in all 4 multi-objective synergy spaces. That's pretty exciting. Unfortunately, if you take a look here, these doses are really, really, really big. So chances are, yes, maybe we would be able to get really good effect. So color gives the TGI, so tumor growth inhibition of the combination. The super yellow would be full elimination. Yes, we can get some nice output here, but it probably will be way too toxic. So if I were making a decision for this cell line, I would say this is a no-go. Okay, now let's try applying it to the second set of data, 1299. So same plot. This is our original protocol that they used. And now we'll look at the doses that appear on all the Pareto fronts here. And this looks much better. So you have reasonable doses for 1299. As you can see, the predicted optimal set of doses of pembro is actually much smaller. And for bevacizumab, it's a little bit larger, but also not that much. So again, in a world where I made decisions about this, I would say yes, for P53 negative tumors here, we should continue exploring this combination. And then test it out, of course. You can also build Pareto fronts as a function of spacing between doses, so you can check different protocols. So the way that you read this plot, these numbers on the left is the spacing between pembro doses, on the right is the spacing between beva doses. And as you can see here, interestingly, closer spacing seems to give much lower combination indices, so higher synergy. Because so in these examples before, we were fixed in the protocol, we were just varying the doses, but here we can also vary the protocols. And as I said, closer spacing seems to be better. Interesting. Something in a world of testing things out. This is a testable prediction that we can now go and take back to the lab. Okay, so how would you apply this to some kind of novel combinations of two drugs? Just to clarify, this method is if you pre-selected your drugs and want to find the best way to combine them. If you want to help selecting the drugs, there's actually a complementary method called musyc, and it has even an online GUI. It's pretty exciting, but this is not the question. I want to select combinations of pre-existing drugs. Okay, so what do I need? I need PK for all the drugs. Obviously, we saw that. And I need a minimum of 4 cases. I mean, 4 more would be better, but at least 4. Control, 2 monotherapies, a minimum of 1 dose of each. Again, more is better, more confidence in parameterization, at least 1 combination. With this, once you have your data calibrated model, it can now be inserted into our MATLAB code, which is available at this link in this paper of ours. And you can figure out your doses and combinations and test them out. Okay, so this paper is published. It came out a few months ago in CPT PSP. This was done during Jana's sabbatical in my lab at TMD Sirona, which was extremely exciting. And if you end up running experiments, applying this, I don't know, want to talk science, have any ideas, do reach out. We would love to see the applications of this method beyond this theory. Thank you.